back to a lecture series on hydrogeology. So, in this lecture, what we are now going to discuss about the specific yield. So, the specific yield, the term it comes that the yield of the water given by a rock. Uh, that normally we speak about the yield in terms of agriculture production and all. Similar to this, for the water, suppose if you take an aquifer, then you will have to assess that how much of water it can give. So that is called the yield, specific yield. So this comes first, depends on mostly of what are void spaces present in the particular rock. If the rock shows more pore spaces, that is more porosity, naturally it can store huge amount of water, and then we will be able to get the water by means of gravity or by pumping. So the first point what we have to keep it in our mind that if the rock has more void spaces, obviously it can hold large number of water. That is the first point. If large number of water is there, either we can get it on its own by gravity. Suppose if you don't need to lift, you can keep it on the top and then check whether the water you will be able to get it, or against to the gravity if you want to take the water which is available in the particular aquifer, that is called by pumping. The part of the rock, the part of the water which stayed back because of the molecular attraction between the two grains, that is called retention. Now let us see in this discussion about the yield. Normally how this is being represented, it is represented SY. The water removed from unit volume of aquifer. Normally the test will be conducted by 1 meter by 1 meter square. You take the sample and then assume that you cover all the sides, leaving on the top and bottom. You take 1 liter of water and then just pass on the water from the top, and then you collect the water at the bottom. It's like how we do the assessment of permeability. Here, if you the known amount of water which is passing, and then the amount of water which you are collecting, and then if you know the volume of pore spaces, you will be able to assess what is the yield. So it is expressed pumping aquifer by gravity. Normally we allow the water to pass by on its own by gravity. That is called the yield. It is expressed in terms of the ratio of volume of water draining out the aquifer to the total volume of aquifer. Normally, whatever, if you take the porosity is being calculated with respect to total volume of the rock. Similarly, the draining which controlled by the amount of pore spaces. With reference to the different formation, percentage of yield may also be variable. In the case of fine grained sediments like clay, the percentage of specific yield is very less because it has higher porosity, but interconnection between the pore spaces in clay is less, as we have discussed in the other essay. Like that here, because of the less connectivity, the yield is less. But in the case of very coarse sediments like sand and gravel, the specific yield is normally high. So this is a graph how a clay, sand and gravel will behave. In clay, I mean the specific yield is low. Slowly the specific yield is increased in sand, and in gravel it is high. If a specific yield graph goes from bottom to high, there it has I mean reverse relation like specific retention. In clay, it is not leaving the water is stayed in a particular clay formation. That's why normally we use shale or clay for the agricultural practice, because it holds water for a very long time. Retention, where the yield is less, their retention will be high. Where the retention is low, their yield will be high. So here because of the molecular attraction is very low, because of yield is more, because gaps are interconnected with each other. Gaps are also more void spaces. I mean the space between the grains and grains distance is more, so that the pass per centimeter per second, it will be more with respect to yield in gravel. So this is the calculated specific yield of different rocks. In shale it is 0.5 to 5. In limestone it is 0.5 to 5%. Both are almost same. and in clay it is between 1 and 10 percent. In sandstone it is 5 and 15%. In sand 10 and 30%, 10 to 30%, and in gravel it is between 15 to 35%. The specific yield is determined in the lab by simple experiments. As I said, you can take the samples and then you allow the water to pass on from the top, allow the water to drain by own gravity, and then assess the volume of the sample and volume of the water collected, and then you will be able to assess the amount of water retained back. So normally this is being calculated. Specific yield is equal to porosity minus volume of water retained. You have to add these two. One normally you will be able to get your specific water retained is called nothing but specific retention, and if you take the whole porosity minus water retained, then that is the specific yield. So it is the ratio of volume of water drained under gravity to the saturated rock. Specific yield, in other words also, this can be called volume drained VD over total volume. This is the rapid drainage, this is moderate drainage, this is slow drainage or no drainage. In a gravel, as I said, openings are more, all the openings are almost connected each other, so that the pass from the top to bottom is more. Wherein in fine sand it is in between, and in clay it is very low. Porosity is high, interconnection is less. That's what they have given in coarse sand, coarse grind sediments. It is between 20 to 35%. In fine grind, it is between yield. It is only 5%, or sometimes it is very less. If it is coarse sandstone, can have specific yield that are closer to the actual porosity. Whatever the porosity, porosity and the yield will be almost the same. Pore spaces, if it is 40%, you will be able to get 35% as the yield. Here the material is shale are likely to have specific yield of 5% only, similar to that. Factors which affect the yields are grind shape, distribution of pores, compaction, and time of drainage. Grind size, as you know, these are the examples of various grind size. As we have studied the granules, very coarse sand. You can visualize that. Of course, this we have seen on the ground surface. Medium sand and silt. The grind size gradually reduced. The scale is given on the top of it. Very fine sand and fine sand. And as we know that the porosity will be high over here and the yield will be high over here, and similarly if silt and clay, very fine sand and fine sand, here the cementing material is also plays a major role on arresting the movement of water. In turn, it will reflect the permeability of the particular area or the yield. Permeability in terms, it comes to your yield also. If the grains are angular, subangular, subrounded, and rounded, again we have discussed the grind shape controls, because the grind shape plays a major role when compaction comes. If the compaction comes, irregular grain size material will pack together, whereas rounded material, know that there are two arrangements like cubical arrangement or rhombohedral arrangement. There, the pore spaces are high, permeability are high, yield is also high. And distribution of pores in a mineral grain like sandstone, you can find the distribution is high. In minerals like granite, because over only the cracks, fractures, the pore spaces are less. Again, the yield is relatively less. Compaction, it is by means of pressure on both the side, increased pressure on the top or from the bottom. It leads to reduce the pore spaces, in turn permeability, in turn yield. And time you are allowing the water to penetrate down. In clay, sometimes it takes 2 days. In gravel, it takes only few centimeter, few second per centimeter. So this is how the factors which will affect the yield. And the following table shows that the percentage of specific yield: 23 percentage on gravel, that is coarse medium. Medium it is 23 to 25 on gravel. Sand between 23 to 28, silt 8, and clay, you can see yield is very less because the transmission is less. That's why the yield is also is expected to be very less. And in sandstone, fine grained 21 and medium grained 27, and in limestone it is 14%. Dunes and 38%, Louises 18%, peat 44%, schist 26%, silt stone 12%, till prominently if it is silt, sand and gravel, it varies between 6 to 16, and in tuff it is 21%. So this is referred from after Johnson. A characteristic closely related to the effective porosity. This is another terminology normally everyone is using. Effective porosity is the specific yield of the aquifer, which is the volume of water per unit volume of aquifer that can be extracted by pumping. Specific yield is clearly an important factor in water availability. Yes, without yield we cannot without water, without yield, the water has to be taken out from the rock. Then only we'll be able to get good amount of water for our survival. It is a factor that is used to convert saturated thickness. This is called another terminology, saturated thickness, to the actual volume of groundwater. The volume is calculated with respect to area into saturated thickness into specific yield. So this is the diagram is represented here. The diagram it says a schematic illustration of an aquifer, which the total porosity in the saturated zone is 30%, half of which is tightly held in small pores of or mineral associations. And total porosity is calculated like, this is the total porosity is equal to a small amount plus bigger amount 30% effective porosity. If you calculate, take only the 15%. This is unsaturated, this is the saturated thickness, this is the total porosity. If you just remove and then check total porosity, the 30% of total porosity, total moisture content, it is coming here, and 15% if you minus from the total pore spaces, it is only 15% is your effective porosity. So this is how normally we measure. You take a piece of aquifer, you just remove it. Assume that you are keeping it in the lab, and then this is the initial water level, and this is the present water level. This is the unit which declined the water which is released and then taken by own gravity. And this method is being normally used in a confined, unconfined aquifer, how that this is behaving, in confined aquifer how this is behaving. So this is how we normally measure the specific yield of the particular field. So with this, the discussion of specific yield is now come to an end, and then thank you very much.